Hello everyone, my name is Frank, and today I'll be going over how to do CS70 Homework 1, Problem 5. So for part A, we want to find a function, f of n, such that n factorial is theta of f of n bits long. So in other words, what we want to do here is we want to find how many bits are inside n factorial, okay? How many bits are inside n factorial? Now, one principle that's important to remember is that if I have a number x, the number of bits inside x can be written as log x, okay? So the number of bits inside n factorial is basically given as log of n factorial. All right, so let's try to expand this out and see how we can simplify the factorial term. So we know that factorial, right, is defined as the product of each of these terms, etc., all the way to 1. And we also know from the property of logarithms that you can split up all this multiplication into the sum of individual logarithms. So in other words, this is equivalent to log n plus log n minus 1 plus all the way to log 1, okay? So that is basically how many bits are inside n factorial. So now we want to find a theta bound for the number of bits, right? And we recall that we can find an upper bound for this and a lower bound for this. And if both the upper and lower bounds equal to each other, then that provides us with a theta bound. So let's start by finding an upper bound. So we see that in this summation over here, each term in the summation is less than or equal to log of n. So one reasonable upper bound for the value of the summation is log n plus log n all the way to log n. And we have n terms in the summation, right? So just to recap what I did, I took our original summation and recognizing the fact that every single one of these terms within this summation, right, is less than or equal to log n, I just replace them all with log n, and that gets me an upper bound for the value of this summation, right? And the value of this summation is pretty straightforward. We have n terms, each of them is log n. So therefore, this summation is n log n. And we have just derived that the upper bound for this summation is O of n log n. So now that we have an upper bound, let's try to derive a lower bound. And there's multiple ways I can go about deriving a lower bound, but one possible option is this. So we know n factorial, right, is equal to n times n minus 1 all the way to 1, right? Now let's consider this product instead. N times n minus 1 all the way down to n over 2, okay? So let's see. So this product over here, right, which I'm wrapping in red parentheses, is clearly smaller than n factorial because I'm not multiplying all the terms that are present in n factorial, right? So then, if I go ahead and take the log of this red product, it should represent a lower bound on the value of that same summation from earlier, okay? So let's go ahead and do that. So again, applying the property of logarithms, we know it's the same as log of n plus log n minus 1 all the way to log n over 2, right? And log n over 2, if we apply the property of logarithms, right, and assume base 2 for this logarithm, that is just the same as log n minus 1, okay? So now we see that inside the summation, right, every single term inside the summation, I'll write this down, every term in this new summation is greater than or equal to log n minus 1. Okay. And we have n over 2 terms in the summation. Why is that? Because we're multiplying n minus 1 all with n over 2, right? So there are n over 2 terms in the summation. So therefore, a lower bound for the summation is going to be n over 2 times log n minus 1, right? Because you're lower bounding every single term in this summation with log n minus 1. And so now this just simplifies to, once again, O of n, I'm sorry, not O this time, it's going to be omega this time. Big omega of n log n. And the reason is because you're going to drop constant factors in orders of growth. Okay, so now let's see what we've come to here. We have big O of n log n, and we also have big omega of n log n. So since we've shown that both the upper and lower bound are n log n, the overall runtime is theta of n. I mean, sorry, not runtime. The overall number of bits is theta of n log n. And that's the answer to part A. So now let's move on to part B. Give a simple algorithm to compute n factorial. You may assume that multiplying 2 bits together takes 1 unit of time. Okay, so let's do part B, right? Let's just go ahead and come up with a simple algorithm to start with that will calculate n factorial, right? And a simple algorithm we can do something we've learned from 61A. So we can write def a factorial function that takes an n, okay? I'll say result is equal to 1, and now set up a for loop. For I equals 2 to n, I will do result times equals I. And finally, I will return result in the end. So this is a pretty straightforward, simple algorithm for calculating n factorial, right? So now what we want to do is we want to evaluate the runtime of this algorithm, okay? So one thing that's important to remember is the runtime of multiplication, of bitwise multiplication, right? So what you'll recall from your textbook is that multiplying a number with, or I'll say having a bits with another number having b bits takes O of a b runtime, okay? So let's look at how much time it takes to do all this multiplication here with our function, right? We know we have O of n multiplications to perform here. And why is that? That's because we're multiplying n times n minus 1 times n minus 2 all the way to 1, right? So that's O of n multiplications that we want to perform here. And how long does each multiplication take? Now, this is the tricky part, right? So the longest multiplication is the multiplication when we have to multiply n minus 1 factorial with n, right? You could say this is like the last multiplication that we need to do. And this multiplication is going to take the longest because n minus 1 factorial is quite a large number, right? As a lot of bits, right? And we know from part A that n minus 1 factorial has roughly O of n log n bits, right? That's just applying the results from part A. In part A, we saw that n factorial was n log n bits. So it's safe for us to say that n minus 1 factorial has O of n log n bits, okay? And how many bits does n have? N has O of log n bits, right? So this very final multiplication therefore takes O of n log squared n runtime, okay? So what I'm going to say here is that O of n log squared n time is required to perform each multiplication in the worst case. Now you might be wondering, don't some of the multiplications take less time to multiply? And that's absolutely true. For example, multiplying 1 by 2 takes much less time, right? But we're saying the worst case of multiplication will require n log square n. And the reason because the biggest multiplication we have to do takes O of n log square n time to do. So when we do this runtime analysis, we're going to say that every single multiplication takes a maximum of n log square n runtime to complete. Okay, so now we're basically almost done, right? So the overall runtime is O of n times n log square n. And that's because you have n multiplication operations to do, and each multiplication operation takes this much time. Therefore, the final answer is simply O of n squared log squared n. All right, thank you for watching.